So another concept when dealing with work, and something that we spend lots of money and lots of time studying in the world in general, is this idea of efficiency. Now, there's several ways of looking at efficiency. There's looking at efficiency referring to thermal properties and heat and temperature. And there's another way of looking at efficiency that's based strictly on work. Now, efficiency when we talk about work is actually really easy to calculate. Okay? So when we talk about efficiency, that's nothing more than the ratio of input and output work. Okay? So we say work output divided by work input times 100% will give you the percent efficiency. It's really that simple, and it should be. When you talk about efficiency, you're talking about the amount of work that you're doing to get a product out or to get something done. Now, this is as simple as to take a lever arm with a pivot point. Okay, take that lever arm and apply it there. I apply my force, I get my displacement, I get a force back, and its displacement. Okay, and the ratio of those two things, force times displacement over force times displacement, gives me the efficiency of that. The other way that it's expressed with the idea of work is using the topic of energy. Now, we haven't covered energy yet, but I'm just going to do this out of completeness. You can say it this way: energy out divided by energy in. Okay? The exact same principle. As a matter of fact, energy in should be replaced with work in. Okay? So the amount of energy that I get out of a system divided by the amount of energy that I put into the system times, of course, 100%. That's all efficiency. What am I putting in there? What am I getting out there? If I get 98% efficiency, which is excellent, that means for every 100 joules I'm putting into the system, I'm getting 98 back, and 2 are wasted somewhere else. Now, it doesn't go away. I mean, energy isn't destroyed. It's just transformed. More than likely, that other 2 joules of energy has gone into something like thermal energy, sound energy. Whenever you have a pivot point, if you have bearings in there, those bearings heat up. Okay? That requires energy. Cool? So that's efficiency in work. Work out divided by work in times 100%. Obviously, work out is never going to be greater than work in. Work out is probably, well, never going to be equal to the work in. Law of thermodynamics in that case. So this number should always be smaller than this number, always giving you a percentage smaller than 100%. Okay? And typically when you talk about efficiency, when you talk about work in and work out, you're talking like an automobile is something like a range of between 10 and 20% efficient. Not terribly efficient. The human body is somewhere in that range too. I mean, not a terribly efficient system. Now, some other systems, like talking about the Chevy Volt. The Chevy Volt does something different to improve its efficiency. Instead of transforming its work in directly into work out, which is the kinetic engine, the motion of the wheels, what it does is it takes its work in, goes through an engine, but that engine is only designed to do one thing, to generate electricity. That electricity goes to the electric motors, which drive the wheels. Now, electric motors are far more efficient than our mechanical motors. If you think about the wheel on a car, there's gears and gears, transmissions, all sorts of stuff that are spinning and rubbing against other things and generating heat. Electric motors are far more simpler. There's really only the axle that's rotating. Okay, so less parts, less places to dump heat, more efficient. So that's why a vehicle like the Chevy Volt is it's a better choice for transportation needs because it isn't turning it into thermal energy. Well, some of it is, but a great deal of it is not being transformed into thermal energy. I mean, there is some. I mean, there is a gas motor, there is a combustion motor in those things, but that combustion motor is a high efficiency, low torque motor. It's not designed to drive the car. All it's designed to do is generate electricity, and because of that, it tends to improve the efficiency. There isn't exchanges. There isn't a gear on another gear to increase the torque put out. There's none of that. All of that is avoided. All it's designed to do is to generate that little energy, so there are electrical energy. There's very little moving parts. But I digress. I keep going off on tangents. So efficiency, really simple. Work out divided by work in times 100%. Okay? Or energy out divided by energy in. And we can call energy in also called work in. The work we put into the system, okay, is the energy we put into the system. It turns out that work and energy are directly related to each other. Well, it makes sense because work is the transforming of one energy type to another. Anyway, efficiency.